Perfect. So yeah, I'm going to talk about the Lightning Network payment channels and the update layer, which is basically multi-hop payments. And the outline of this talk is one slide, myths about routing that are floating around, and I just want to discuss them in the beginning very briefly. Then I will talk about the payment process on the Lightning Network and compare it a little bit with the payment process on Bitcoin. It's not very technical, but it motivates some stuff of why we're doing stuff on Lightning, how we're doing this. And then I explain how trustless payment can be achieved via HTLCs. As I mentioned before, we do a short break and ask if you really want to see this, because I explain it more technically than when I talk about the SPHINX mix format and onion routing. For those who are already familiar with the SPHINX mix format and onion routing, I don't talk about filler generation and padding. I omit this because I think it's too technical for a talk, and if somebody wants to dive in really deeply, they can. And I think Christian already promised. That's the point. So yeah, let's talk about some myths about routing. So first myth, it's unsolvable. Certainly not true, because currently payments are being routed on the Lightning Network, so it's not unsolvable. It's an NP hard or NP complete. This is plain wrong. I mean, you have to admit, most pathfinding algorithms have a worst case of cubic runtime, but it's far away from being NP complete or NP hard. However, it's still computationally heavy, and maybe if the Lightning Network really grows, it becomes infeasible for cheap or small hardware or low bandwidth devices. So that's something I think we as a community should be honest about, to acknowledge that routing still is a difficult problem. Some people would argue it relies on trust. I would argue that HTLCs operate in a trustless manner, so that should not be true. However, nodes can misbehave to interrupt the routing process. So I mean, if a node is just not forwarding the HTLC and then sending an error back of saying, hey, it timed out or something, you know, I mean, you still need to like trust the people to behave properly in order to everything to work, but they can't steal your money or something. It needs central nodes or routing hubs. That's what people say. Currently, we don't really have research for this on the Lightning Network, but if you look into the research of social network analysis, it suggests quite the opposite, that we don't need those central nodes. And then, of course, there's the other myth coming from the Bitcoin community. It has no problems at all. I would say there's, for example, spamming and delaying of HTLCs is a principal problem that we have in the current construction of the Lightning Network. So I would say there are some problems. And another one is pathfinding that is a little bit difficult, which I will talk about tomorrow a little bit more. So after this talk, you hopefully understand this picture. So right now, you don't have to understand it. Who does understand this picture already? Yes, sure. So anyway, so this is good. And for most people, hopefully there's something to learn. You don't have to understand it now. We're working towards this. So the payment process. So I want to compare the payment process of on-chain Bitcoin and off-chain Lightning Network payments, something that you probably experienced and know. Bitcoin addresses, I would say, are a little bit like bank numbers or bank account numbers, right? Bitcoins can be sent to that address. If I know the bank account number of another person, I can send money to that bank account. I can do a wire transfer. And in Bitcoin, we have this concept of payment requests if you have a Bitcoin wallet. But they mainly only exist for a smoother user experience, right? Because you can already say, hey, I request this amount of Bitcoin, and you can scan the QR code, and then your interface already shows this. But Bitcoin itself does not really have this. On Lightning, however, you, at least currently, cannot really send money to another Lightning node without an invoice, right, which comes with a payment request, unless you do some dirty low-level routing tricks where you drop the amount in a routing fee on a circular route that we just discussed. And I did a video in the past demonstrating this, or you have the spontaneous payment extension by LND. I think it's merged by now, so you can do it, but it's still like using mechanisms like this. But the standard way is to have an invoice. So in Lightning, the recipient or pay first has to issue this invoice, as I just mentioned, and the payer in Lightning pays the invoice in return for a secret pre-image. I mean, that's all stuff that we already know. You could call this secret pre-image also a receipt, right? The proof of payment that we mentioned before. And my question is, maybe already to you, maybe you can already give an answer. What does this have to do with routing and the fact that Lightning is a network? Anybody has some ideas on this? I mean, I'm supposed to talk about multi-hop payments, right? And I start off by looking at the payment process of Bitcoin and Lightning Network and comparing those. So why am I doing this? What does this has to do with the fact that on Lightning we have a network? Yeah.
You need an agreement on some lock mechanism, so the hash lock mechanism.
Yeah. So
what is the value of that?
right. We have the hash time locks, right? And there we have the payment hash that is always in there to fulfill these contracts. And that is pretty much the reason how we do trustless multi-hop payment. But let's look at this in the next couple of slides. So I'm actually happy that we're discussing them, even though they're very high level and non-technical. So let's start out with a cash setting even, right? Not even Bitcoin, start with cash. So let's assume I do a cash payment, right? So what I do, I ask for the price. How much is it? And then the person says, well, it's $10. And then I give the money, the $10, and I get the receipt, or I get the good, or I get whatever I wanted to have for the $10. And from a computer science perspective, this process should be somewhat atomic, right? In the best case, if I want to buy your water, you can hold the water in one hand, I can hold the dollar bill in the other hand, right? It's $10. and we can both like attach to it, and then we can keep loose at the same moment, and we can really make this atomic in the sense. Either the payment occurred and the good was delivered, or it didn't happen, and we're happy with this, right? So that's the concept of atomicity which we get in a cash setting. Let's look at a direct on-chain payment with Bitcoin, right? So if I want to send 1 Bitcoin, I do not really get a receipt or something. What I do is I look in the blockchain if the transaction was being mined. This is my receipt in Bitcoin. Yeah. Okay, yes. Yes, you're right. I could do that. But I mean, the standard use case that people in Bitcoin have.
I'm not doing that.
Yeah. No, so yes, you could do it on Bitcoin, but I was, when I was creating this slide, I mean, actually this one is the one I could skip, but in the standard use case, what you do is you look on the blockchain, you see that the payment actually occurred, right? And to some degree, you could still say it's atomic because either the payment was mined or it was not mined, right? So but there's no such thing in Bitcoin as a half payment, right? I mean, there's an unconfirmed transaction. Yeah, right. Okay, so let's look at an indirect physical payment with cash, right? So let's assume there's a third party, like a bank or another person, that is supposed to help me with my payment, help to forward the payment. I want this to be atomic, right? I don't want this person in the middle to be able to run with the money. And the question is, can it though? Because otherwise we have this situation, I give the $10 to the person in the middle, and the person says, yeah, it's $10 for me, great. It says, yeah, it's great. I don't have a receipt yet, but yeah, no problem. I just didn't get an answer yet. I will do it eventually. Right? So the question is, can we make this atomic in the real world? Right? And how we could do this is we could create a contract, right? Where I'm saying, you know what? I give you $10 if you prove that you have given $10 to a payee. If you do that and we create this contract, I feel pretty confident. Right? So we make this contract. Now the person in the middle says, you know what? We make also a contract. Actually, I mean, they could do it directly, but they could say, I pay you, I give you the $10 if you provide me with a receipt. Right? And these people could set up these contracts. They could, in the offline world, in the cash world, negotiate these contracts. Okay. Yeah, certainly, right? I mean, that's the reason why I'm trying to explain this. The concepts are very like basic and natural or human. Yeah. So you could do something like this. And of course, you could add a service fee where you say, you know what, I give you 11 if you prove this, and if you forward 10. Right? And then this person gets like $1 of a fee of actually having all this hustle of setting up another contract and helping me out with the payment. So then what would happen is this person would actually know it has this contract where we agreed on this. It would give the $10, get a receipt. This is an atomic operation, and then it can fulfill this contract. Right? In this way, we have been able in the offline world to make an atomic process like this. However, I would argue that in the offline world, there are huge risks attached to this process. Right? I mean, you said that in France it already exists for many years. In every country of the world, but you could have a badly written contract, right? Natural language. Let me come to that. I agree with you that you have this, but let's first agree we could have a badly written contract because natural language is just vague in general, right? And then you could have forgery on the receipt. And coming to your point, going to court might be more expensive than the $10 here, time consuming, so you might not go and settle this in court. Right? You're just gonna drop your $10 and say, you know what, I lost it.
I know that the case in France that under soft cap you can't claim can be accepted in a court case.
Yeah.
Under
yeah, it's very similar with HTLCs. Under a certain level, it's dust. Yeah. Right. So as I'm saying, in the real world, this kind of like indirect payment process comes with a huge risk. I would argue that with programmable smart contracts on Lightning, with hash time-locked contracts, this is going to be much better. Right. So what are hash time-locked contracts? Well, it's just a regular Bitcoin transaction with a special script inside. And this special script I refer to as a conditional payment usually. I mean, there's a time lock too, but it's a conditional payment. And the transaction is locked for a certain amount of time. So this amount of time is which it takes to forward the payment and get the receipt. And then the receipt is a secret, random, in best case unique value called the pre-image. And I will use these terms and I guess everybody else interchangingly. And then the hash of the pre-image is called the payment hash. So this can be seen as an identifier for this particular payment, unless we have payment decorrelation where the payment hash will change in every hop, right? But currently we have the same payment hash for every hop in the network. And the thing to note is it's really like a legal contract from the cache setting, but without the disadvantages. Because it's pretty cheaply enforceable by publishing the contract, which is the Bitcoin transaction, to the Bitcoin network. It's much cheaper than our court system, even when we have a fee spike. And it's not really possible to have a misunderstanding because it's a programmed contract. It follows a protocol. Everybody knows how to read these contracts, how to follow this protocol. So there is not really a lot of room for misinterpretation here. So hash time-locked contracts in payment channels. They enable direct atomic payment between two neighbors that share a channel. And nodes build a network, and payments in the networks resemble the situation of indirect payments with cash. And hash time-locked contracts are just there to solve this problem, right? So in the offline world, we had this, but in Bitcoin, we can do it in this way. And on a technical level, HTLCs are just another output in the commitment transactions. I mean, we had this before, right? Instead of these two outputs, we now have several hash time-locked contracts. Coming to the question that you asked before, let's assume one of these HTLCs is timing out. I can still set up more HTLCs for other payments, so the channel is still operational, even though one HTLC might have a local problem at a certain point in time. So the good thing is they can be enforced on-chain if the channel fails, and they can settle off-chain if the pre-image is provided, right? Which was the situation that we discussed before when the later in the route a channel breaks, then the pre-image is seen on-chain, and then the other one can still settle off-chain, which is nice. And before explaining the details of routing, I want to ask, how is the payment hash sent over? How do we do that? You all know this? Exactly. That's the point. We do an invoice, right? Where most of the stuff in Lightning is encoded as Lightning messages that are encrypted over noise, XK framework, Charter, Poly, whatever, right? here we just have an invoice, and we depend on communication between people, right? I mean, I could literally on the telephone dictate the invoice to you, or I can do a QR code, whatever, right? I mean, but Lightning doesn't explain which medium we should use for this part of the protocol. But I was wondering in the beginning when Christian was giving an overview of all the bolts, why he didn't put bolt 11 as part of the multi-hop layer. Right? He said bolt 4, the onion routing, is the multi-hop, and I would argue that bolt 11 also belongs to multi-hop, because this is really the first step, and that's needed to do this, because this is how we transport the payment hash, and without the payment hash we can't set up HTLCs. All right, so that was the first part. I could skip the next one and go to the SPHINX routing right away, so I would do this by show of hands. Who wants me to skip the next part? Perfect. Only James half. All right, so let's talk about trustless routing of payments through a network of payment channels. And again, it's very high level, and then the technical stuff comes in the third part where I'm talking about SPHINX routing. So this is how my Lightning network looks like. So here's Alice, and Alice has a multi-signature wallet together with Bob, right? And the commitment transaction currently looks like 0.35 Bitcoins are going to Alice, and 0.15 Bitcoin go to Bob. So together they have this channel, and if you add these numbers together, I neglect the on-chain fees, they have half a Bitcoin in this channel. And you have a similar situation for Bob and Charlie, only that this channel has a higher capacity. And if you add these two outputs together, you see that Bob has a total balance of 0.65 Bitcoins that Bob owns. So this is my setup. And now Alice thinks, hey, I want to send 0.1 Bitcoin to Charlie. And as you see, I mean, I want to talk about a trustless network initially, but let's talk about a trusting Lightning network initially, right? So Alice thinks, hey, I want to send this money over to Bob. How does she do this? The commitment transaction gets updated, right? So here the balance changed, and now if you add this together, Bob now has 0.75 Bitcoins, and Bob says, hey, I'm very honest, of course I forward the payment, so now this balance is updated, and Charlie now has 0.4 Bitcoin, and Alice has 0.25 Bitcoins, and the payment went through, and everybody is happy. Obviously, we could have the situation, or we do have the situation, how I created this here, that Alice needed to trust Bob to forward the payment, right? Both payment channels needed to negotiate a new commitment transaction for both sides. And we could change the output of the commitment transactions so that routing works trustless, right? That's our goal now. And the idea is, how we do this is we use the BIP with the hash time lock contracts, and we include this in the output of the commitment transactions. So we have another conditional output in the commitment transaction that says, hey, if you can provide me the receipt, you can settle this. And this output technically can only be spent by the recipient, because that's the person who knows the pre-image. The pre-image is sent from the very end of the path back all the way to the sender, and within a certain time frame, because otherwise, if the recipient can't provide the payment, the pre-image to the payment hash after this time frame, the sender can claim the funds back. Right? So basically, on Lightning, what we do off-chain is we remove the HTLC from the channel. Okay. So this is the trustless Lightning network. It starts that Charlie has some hash of some, well, actually a hash of some random value R. I should move the sum, right? But it has this thing, and as we mentioned before, it needs to get this over to Alice somehow, and this is being done by Alice saying, hey, I want to send you some money, please do an invoice. So this is being sent over via an invoice, and what Alice now does is it changes the outputs here in this commitment transaction that spends from this multi-signature wallet. So you see she already removed some of her balance. Before she had 0.35 Bitcoin in here, and now there's this 0.1 Bitcoin that is pointing to this payment hash, or to a script that when you like reveal the pre-image to this hash, any person can claim, right? And Bob still has the old output, right? And Alice thinks, well, if Bob doesn't provide R after the time lock, I can just claim the money back. So no big risk for Alice at this point. What Bob thinks is, well, I can't claim this 0.1 Bitcoin without knowing R in some time, right? So Bob now is really incentivized to say, you know what? This payment is supposed to be for Charlie. I set up an HTLC with Charlie using the same payment hash, because if Charlie wants to have this payment, it can only do so by providing the pre-image to me, and then I can claim this money. And that's the entire idea. And as you can see, Bob now has less money than before, right? Because this money is technically not belongs to him. This money technically is not claimed by him yet, right? It's like somewhere in nirvana, right? And the real money that's really here at this point is there, right? But I mean, obviously, since the CLTV deltas are all fitting together, Bob knows that he won't lose money. But Alice, on the other hand, didn't need to trust Bob that this is really working, or that Bob is working properly. Because if Bob just doesn't forward the payment, then Alice gets her HTLC output back. Well, so now this cloud should be here. Sorry for that. Charlie is like, hey, I need to really get this payment hash back to Alice. So sorry for this wrong pointer. So yeah, Charlie thinks, well, I can only claim this HTLC output by providing R. So Charlie provides R to Bob. And now it's safe to make a new commitment state where Charlie really has the money. So Charlie already is reimbursed, like in the indirect payment setting with cash that I explained in the beginning. And this HTLC is still active. Alice has not really paid yet, but Alice already like lost the funds in order to create this output. And then since Bob has the R value, Bob says, yeah, great. This R really produces the payment hash. So now I claim the funds back from Alice. Yep. It shows up. So the thing is, if we two have a channel, and we don't even do a complex routing process, but I just want to send money to you. The way how we do this, and Fabrice already showed it in his pictures, is we set up an HTLC. I have some slides later. It was your question already in my first talk where I explained how exactly the messages are there on the protocol level. So remember, like last talk, I also started very high level and then it became very technical. So I come to this, but I defer to the future at this point. But yes, the HTLC really shows up. Well, yeah, so if you are here, right? Technically at this point, when Bob says, I want to forward this, Charlie could answer right away, hey, I already know the pre-image, just give me the money, right? But the thing is, I mean, we want to have it in a way where when Bob forwards the payment, Bob doesn't know that Charlie is the final destination, right? For privacy reasons, right? So we implemented it in a way that it's the general case anyway, because then you can do it with the same Lightning messages and you don't have to like do case distinctions. So it's just better to do it in this way. Yeah.
Technically still, Charlie doesn't have to review the pre-image, but if he goes on chain, he will need to review it.
That's the point. So when we're here, Charlie doesn't have to reveal the pre-image, that's correct, right? But if Charlie wants to have the money, off-chain or on-chain, in both cases, Charlie will need the pre-image to either spend this output or to get rid of this output and get the amount of money in his output of his commitment transaction and also the other party's commitment transaction. But we look later in detail how we really update the commitment transactions and how the HTLC output is there. I just ask for some patience. So let's go to source-based onion routing and the SPHINX mix format. And I've heard you have already read some parts of the paper. And I don't envy you because I think it's a very technical paper and incredibly difficult to read. So why are we using the SPHINX mix format? Well, the payer wants to be able to send money without being exposed, right? So it's about privacy. It was, for me, one of the most amazing moments when I set up my first Lightning node and I created a small paywall app, and the first person paid me. And I mean, it's like setting up your first blog or your first YouTube video or whatever, right? You're like, oh, who was it, right? You look in your log files, and I look in my Lightning log files already knowing I won't find anything. And I was like, yeah, I didn't find anything, right? Because it was completely anonymous, as I should have known before, but it was to some degree frustrating to realize that it was really anonymous. And then I was really happy to see, oh yeah, it is really working. So, yeah, sorry, I had to share this story. So the payee doesn't want to be exposed either to the rest of the network, right? So if I want to receive some money and other people are helping on the routing process, they don't have to know that they're actually routing money to me. Then the routing nodes have to be able to send back an error message, right? If something is not working, for example, there's not enough balance or the onion was not formatted correctly because there's not enough fee there, there has to be some way of like giving a response back to the initiator. And the routing nodes should know as little information about the payment as possible, right? So this is the payment hash, which, as I mentioned before, and I think Fabrice already mentioned, it will stop with payment decorrelation. And the routing nodes only know an upper bound for the amount that is being paid, right? If I forward a certain amount, I know that the actual payment is lower because there's still future routing fees included in this amount. But this would also stop when we have atomic multipath routing, because then I only know that this is a certain payment, but there might be other payments on other routes going to this. So I don't even know the upper bound of the payment. What they know is the incoming channel, where the payment is coming from. So not the original sender necessarily, but just my channel on which the payment is coming in, and the outgoing channel on which channel I should forward the payment. Everything else they don't know. And routing nodes want to be able to verify the authenticity of the onion, right? So they don't want the onion that is being processed to have some like weird information. So there's still some HMAX in the onions at every hop, so that routing nodes can actually check that everything is in the way how it's supposed to be. And what the research community will tell you, and I think it's already in the abstract of the paper, is it's a very compact format. It uses only very little amount of data. And yeah, for the coming part, I think you already saw the video, and I think the video actually is a better medium than slides to explain this, but you will see the exact same example. So yeah, there's Alice, and she wants to send 300 Satoshis without a direct payment channel to David. But Alice, of course, knowing the gossip protocol, has a pretty good idea of what the network looks like, and Alice decides, oh, I have a channel with Bob, and Bob has a channel with Charlie, and Charlie luckily has a channel with David. So Alice decides that she wants to use this path to send a payment, and there's short channel IDs because we later need them in the onions, and I didn't use the full-length short channel IDs, but just some short ones to make it easier to talk about them and refer to them. So we start creating the onion starting from David. So if Alice wants to create a payment, Alice begins at David's point. So we create an onion starting from David. And the interesting thing is, in the onion itself, there's no payment hash inside. I was pretty surprised to see this. The payment hash is transported in a different manner. But what does the format of the onion look like? Well, we have a header, and there's a version byte in it, because we might have different versions of the onions. So there's a 33-byte compressed public key inside of the onion, and we will in a few slides see why we actually need this key. It's used for Diffie-Hellman key exchange. The interesting thing is, it's not the sender's pub key or node ID, right? Because if it were the sender's pub key, the sender would be revealed. Right? So it's a different one. But it's an ephemeral pub key from the sender for David. So the sender generates a new key pair specifically to use for this payment with David. And from this key pair, the sender sends the pub key over to David. Then there is a payload in the onion. So the payload consists of 1,300 bytes of hops data. And this boils down to 20 times 65 bytes. So you can have a maximum of 20 hops on the onion. Right? There's no longer paths permitted in the Lightning Network currently, even if the network would grow, it has a larger diameter. And each hop needs 65 bytes of data. The first one is the realm, which is currently set to 0. It's kind of like another version in there. Then there is 32 byte per hop payload, 32 byte of an HMAC to verify that this particular per hop data is the one that's supposed to be there. And then there is some filler in the payload. And as I said, I won't discuss the filler completely. And once you have the header, the payload, then you have another HMAC for the entire onion to verify the integrity. So the question is, what kind of data do we store in the per hop data? We store the short channel ID, the amount to forward, the outgoing CLTV value, and then some padding, which we might use later for other information. So we already put this here for future backwards compatibility. Right? And as you can see, there's in this data that we use in the onion, there's nowhere the payment hash included, which again, I think is a little bit remarkable that it works without it.
It's currently not spec'd out. There's two proposals that would place that either in the payload for the final hop, or we have a new trick that we can use the shared secret that we use to decrypt it. So that's a shared secret between the sender and the recipient. We can actually use that to derive whatever secret we need. And since that's basically a random secret that is randomly generated, we can also make that derived from some shared constant. No, not really. All we need to do is inside of the onion signal, hey, you're the final recipient, and use this protocol to derive
So the shared secret could already be like the pre-image basically, and then if you hash it, it's the payment hash right? Stuff like this. But you could even have an inner onion where you don't have to hash it twice. And signal in the realm that this onion is the last one. Hey, there's a lot of possibilities. I'm just saying this. So yeah, it's not spec'd out, as Christian says. So the per hop payload for David, simplified, looks like this, that the short channel ID is set to 0, which signals to David, hey, you're the last hop. There's no other channel you put it to. The amount to forward is 300, which means you receive 300 Satoshis. And then there's an CLTV value. And I think for the last hop for David, you could also set it to basically whatever, because there's nothing happening here anymore. And then what is happening, as I mentioned before, there is this ephemeral key for David. And this part here is encrypted by doing a Diffie-Hellman key exchange between the private key that belongs to this ephemeral key, and the private key is known to Alice, and David's public node key. Right, and this is nice because David now with this, with his private node key and this public ephemeral key, can also create the shared secret. And if that was too quick for you, I will actually talk a little bit about sharing a secret between Alice and David. So this is now very mathematical. I desperately wore my Pi shirt today because I'm a mathematician instead of a Lightning Network shirt, because I knew I have this in the next slide, which you see me smiling already. So let G be a generator point of our elliptic curve of prime order, right? So we have an elliptic curve of prime order P, which is always a cyclic subgroup of prime order. And we have A and D are basically integers smaller than P, which we call private keys for Alice and David. And now we can derive the public keys, right? How do we do this? We multiply our curve point by A, which basically means we add the generator point A times to derive our big A, which is the public key. And we can do the same for David. And these are the static node IDs for Alice and David. Now, the elliptic curve Diffie-Hellman key exchange says that A times D, so small a times big D, is the same as small d times big A, and this is our shared secret, which we can use for symmetric encryption. So I want to do a mathematical proof with you to see that this equation actually holds. And the fun thing is it's a very easy, simple mathematical proof. So it starts with AD, right, which is the left-hand side of our proof. And by definition, we know that AD is the same as A times small d times G, right? This is just the definition here. And then we can use the law of associativity, and we can basically move these parentheses over here. And then since we have integers, which we multiply with each other, we can use the fact that these integers are actually living in this group, which is an abelian group, so we can flip them around. So now we have D times A times G. We use the law of associativity again, so now we have D times AG, and we can plug in the definition, and here we go. We have proven that AD is the same as DA, which is extremely cool. No, it is. It's, I mean, honestly, think about it. You can just by knowing the public keys of other people and multiplying your own private key, you have something that is a shared secret, a shared value that only you two can know, right? I mean, this is part of the properties. Only Alice and David can know their shared secret, right? A third party cannot just multiply some value with their private key because it will be a different equation here. It will result in a different curve point. And the shared secret, as I said before, can be used for symmetric encryption then. And once the public keys are known, Alice and David can independently compute the shared secret. They don't even have to communicate anymore, right? Which is also extremely cool. Yeah, and that's the second mathematical slide. A short intermezzo for math nerds about the discrete logarithm, because I think everybody who is interested in, you saw this last week already, right? Discrete logarithm. All right. I mean, I'm strong to say that everybody should really be aware of this, because this is where the entire worth of Bitcoin comes from, right? As soon as we solve the discrete logarithm problem, Bitcoin basically instantly becomes worthless. So EC is an elliptic curve. It's a group, and it's homeomorphic to Z modulo Z modulo PZ. And ECDSA and the Diffie-Hellman key exchange heavily use the following homeomorphism. So homeomorphism is a map that goes from this group to this group. And how does this map look like? Well, we take an element from this group, which before we called an integer, or usually people call it a private key, and we map it with the map H to A times G, which is our point on the elliptic curve. Yes?
I mean, you can still lock your phone with a
Yeah, that is true, but
yeah, it could break a lot of.
Yeah, I mean, I'm pretty sure if I would solve the discrete log problem, or anybody else, they would destroy Bitcoin right away. It's, I mean, first of all, they could steal a lot of funds. They could go to an exchange and then exploit it, and it would work very quickly. And afterwards, everything.
Break the signature scheme, but doesn't break the proof of work, which is maybe the main component of Bitcoin.
Yeah, but you can steal a lot of coins.
Yeah, sure.
Yeah. No, I mean, there's other ingredients, right? But I mean, the discrete log is the core assumption upon which Bitcoin currently builds its security model, right? I agree with you that former transactions cannot be reversed, but I mean, if you can steal them, what good are they? Yeah. So anyway, the elements in this cyclic group are called private keys, and the elements in the elliptic curve are called public keys, right? And by construction and math theory, we know that H is not only a homomorphism, but an isomorphism, which means that H is bijective, and an inverse map H raised to the -1 power does exist. We already know from mathematical theory that it does exist, which is a little bit scary if you think about it. Because as I mentioned before, if we would know how this map looks like, we basically could compromise Bitcoin. So the fun thing is, this inverse map is unknown unless we compute H for all elements of this group. And we start with this group to be so large that we say it's infeasible to do this with a computer, right? Because we could not even store all the elements because we have like way too many elements there. And the funny thing is, I was just recently in my old university talking to some professors who are actually working in algebraic geometry, and I asked each of them, why is the discrete log problem actually difficult? And all of them told me, we don't even have an argument for this in math. We just know it's difficult. But there's no like deeper mathematical theory that they were aware of why this is a complex problem.
It wasn't called a problem. That's why it's a problem. Like discrete logarithm problem.
No, but there's other.
We don't know the solution, but there might be a solution. We could have proven that it's unsolvable.
Well, the thing is, we already know there is a solution. We already know it exists, right? We just don't know a construction to analytically create this, right? I mean, computationally, we can already do it. Yeah, I mean, even in linear time. I mean, we have to do it for each element in the abelian in this group, right? And I mean, knowing this map in this direction is ridiculously easy, right? Yeah. So. Giving an analytical closed formula for H for the inverse map is called the discrete logarithm problem. So going back to that, we use the Diffie-Hellman key exchange and this stuff to create a shared secret between the private key that belongs to this ephemeral key and the public key that belongs to David. And David, obviously, with this public key and his private node key, can decrypt this onion. Right? And nobody else on the route can decrypt this onion. So this is what the inner part of the onion looks like. Now we look at the payload for Charlie. Charlie now has an increased CLTV delta. Charlie still forwards 300 Satoshis because Charlie is paying David, and David is supposed to get 300 Satoshi. And the short channel ID tells Charlie, please forward this on this channel. And again, Alice generates a new key pair, an ephemeral key pair for Charlie with the same trick, encrypts this entire blob. So we are there. And now we look at the payload for Bob. It gets a little bit repetitive, but for Bob, something changes a little bit. Bob now has an amount to forward of 301. Why is that? Yeah, but these are not Bob's fees. Yeah, Charlie wants fees, right? So Bob is forwarding 301 so that Charlie can forward 300, so Charlie gets 1 Satoshi in fee. Right? But this is where the fees are actually really encoded into the onion. They're not explicitly there as like, here's your fee, but it's just the difference of the amount to forward values on there. And yeah, this gets encrypted again. And then, of course, Alice has to set up an HTLC to Bob, right? But this is not part of the onion. Yep.
41, 18, and 9 is the
yeah. Exactly. So as we mentioned, they have to be decreasing along the path. So interesting enough to know is that the onion is constructed from Dave to Charlie to Bob to Alice, but now the HTLCs have to be set up. This goes the other way around. The HTLCs are set up first from Alice to Bob, then from Bob to Charlie, and then from Charlie to David. And then the pre-image again is released in this direction. Yep.
So the CLTV delta, who creates that?
Yeah, Alice is creating this entire onion, and Alice is defining all these values here. So what Alice does is, it looks at the gossip protocol, what the CLTV deltas are for each channel, and she's just basically adding them to them. Right? So for this channel, there's a CLTV delta of 9. So since we started with 9, she's adding another 9, so now we have 18. Right? And then comes, I don't know what this was, 23. Yes, exactly. So what could happen is that the onion later on is transported at some point to Charlie. Charlie looks at what she's doing there and says, no, the CLTV delta or the fee is too small, and then an error is being reported back. Right? So yeah, this can happen and will happen and does happen. Right? In particular, when Charlie changes the channel parameters, right? An update message is sent over the gossip protocol, as we will see tomorrow. And meanwhile, an onion could already be on its way. So then it arrives at Charlie, and Charlie says, no, this does not fit my parameters anymore. Yep. From the Oh, maybe I did a mistake. I mean, it happens all the time. But as far as I understood, the time lock needs to be decreasing along the route. Yeah. Right? So in case that this thing settles on chain, Charlie still has enough time to turn around, as was the wording, to go to Bob. Right? So the CLTV deltas are the time locks that are being used.
So you can start at the end.
The fees start at the end. We will see this tomorrow. Well, I mean, you start with this low CLTV. I mean, you could start in the beginning and say the CLTV is 1,000 and you always decrease by the deltas. But what could happen is then you go to the negative. Right? So and since you construct the onion from the end anyway, yeah, but for the fees, there's actually a different reason why you look for the fee. Yeah, okay. So some notes on the presented simplifications. The onions themselves are the payload of the update add HTLC message. And that is answering your both questions from before. We will look at this afterwards, but this is really where the payload, where the onion is transported. The message, the update add HTLC message also contains the payment hash, and the message offers an HTLC with an actual amount. So usually the nodes offer the amount that they are supposed to forward. I mean, they could mess around with this, but probably then the routing process will fail, right? Because either they forward not like less than they're supposed to forward, and then the other person doesn't have enough fees, right? So why would they do this? And Alice constructs the onion and uses ephemeral keys for every hop. And the onions are encrypted with a Diffie-Hellman shared secret between them. And as I explained before in detail, the hops and the key generated by Alice, and the hops node static key. And the onions are always 1,366 byte in length. So even at the last hop, right? So if you looked at the picture, the onion was always getting longer. But as I said before, I'm missing out this filler generation of making the onions always a certain length. So the onions are packed with junk data, and yeah, we do this to for privacy reasons, right? We really don't want a node at the end of the route know that they are basically the last or the second last hop. Okay, so let's go back to bold 2 and the update layer. But I didn't want to do it before we are in Multihop, so we talk about the normal operation of a channel, right? So in my last presentation, we already talked about how to establish a channel and how to close a channel. Now the question is, how do I actually send money forward to somebody? So the picture that you always see looks like this. There are update add HTLC messages that contain onions, and we saw how the onions look like before, right? They have some amount to forward, they have some CLTV deltas, and they have some channels on which to do this and some keys. And they could go back and forth in both directions, right? Arbitrarily oft. And then at some point in time, we have commitment signed message and a revoke and arg message. And we're going to see how these messages are actually being sent back and forth and why they are being sent back and forth and how this actually really locks these HTLCs. So there are basically 5 stages for an HTLC to become valid. And this is just basically, well, let me just skip this slide. I do it visually afterwards. So this is just for your reference to see it written down. So let's start here. We have Alice, who has her commitment transaction to A, and we have Bob, who has his commitment transaction to B. And you can see in Bob's commitment transaction, the output to Alice is a regular output, where the output to Bob is the RSMC, and here it's vice versa. The regular output goes to Bob, and the output to Alice herself is the RSMC. And Alice wants to offer a payment to Bob of 15 millibitcoin. And sorry to Fabrice for repeating something that you already explained, but I think it's worthwhile seeing this again. So Alice wants to offer a payment to Bob of 15 millibitcoin. And when you remember my first talk, I basically said there's a new stage where it's already like at the other side and they somehow like end up there, but there's actually more state in between. And how does this look like? Well, there is an unsigned commitment transaction that Bob creates now. Alice sends the update add HTLC message, which contains an onion and a payment hash. So Bob can create a new commitment transaction and add this output, right? You see Alice already has less money than here. And this money is sent to this commitment transaction, to this HTLC output. It's still unsigned. Then Alice, at the next step, sends a commitment signed message to Bob, which means that Alice already knows what's the next per commitment point that was in the opening channel message, and in other channel messages here, they will also exchange the next per commit point. So she can produce a signature for this transaction. Remember, it's a 2 out of 2 multisig wallet that is being spent. So she's producing her signature, and obviously Bob can produce his own signature. Right? So now at this situation, Bob has actually 2 valid states. There's nothing revoked yet. Right? Bob could technically still publish this state without having any penalty. Right? Only thing is Bob has no incentive to do that. Right? Here Bob is getting money. Here Bob doesn't. So why would Bob? But he could. So now there comes the revoke and UCK message that Bob is sending. So what Bob does is he revokes his transaction over here because he says, well, this one is better to me anyway, and the entire channel operation protocol doesn't forward if I don't do it. Right? So Bob now shares the revocation key for his revocable sequence maturity contract. Right? So he can still publish this. Miners would mine it, but then he would lose all his funds. Right? So now it's revoked. Alice, meanwhile, creates her own commitment transaction. Remember, both parties have their own commitment transaction, but this one is still unsigned. So Alice needs to wait. Oh, question. If we are in this scenario, and Alice has the idea of publishing this commitment transaction, why is Bob not losing money? Yeah, so I mean, if you think about it, this is one state, and this is the next state, right? And this state is happening by Alice wanting to send 15 millibitcoin to Bob, which here Bob seems to kind of already have, right? At least the output is here, and Bob knows if he can provide a pre-image, he can get this money, right? So yeah, I mean, she has not revoked her commitment transaction yet. She could publish this. Is this a problem for Bob?
Still has
Yeah, that anyway, but Fabian, you raised your hand before. Yeah, but let's assume we're doing this for routing. That's the point. That's the important point. Right? Bob does not forward his HTLC yet. That is really important. If Bob would have forwarded his HTLC and somebody would already release pre-images and would ask from Bob, hey, I want to get reimbursed on my HTLC, and then Alice goes and publishes this one, Bob effectively loses this HTLC output. Right? So the routing process at this point cannot proceed. Right? So technically at this point, Bob already does not really have this. Right? I mean, if Alice becomes unresponsive, no big deal. Bob can publish this commitment transaction. That's no risk for Bob, because if the timeout is really happening, he can claim, that's the HTLC for Alice. So yeah, I mean, Bob has his 20 millibitcoin here, right? Nothing bad happens. So yeah.
Why wouldn't Alice publish the revocation key and publish the transaction that was revoked?
This one,
Yes.
this transaction, Alice never sees.
What is never seen?
So Alice can construct this transaction, right? And in the same way as Alice can construct this transaction, she never sees it signed, right? Because she doesn't have Bob's key to sign this. Bob never sends over his key. He only sends over the...
Only if Bob publishes it, she can use the revocation key to take
Yeah,
it.
that's the point. That's the point. Only if Bob publishes it, because Bob has a really fully signed transaction. Then she says, yeah, okay, the Bitcoin network obviously accepts it. But then she says, hey, I can claim this output. This is really how it's working. Okay, I thought you were also... Sorry. Okay, so how does the protocol continue? Well, Bob sends his commitment signed message, right? So this goes pretty much in your direction, which means Bob now sends a signature for this commitment transaction, right? And again, Bob does never see this entire commitment transaction signed unless there is
Just his part.
his part of the signature. Alice, yep. So now this is how the protocol looks like. This one is revoked. Alice still is able to publish this one, but Alice really wants the payment to go forward, right? Maybe she already has set up an HTLC incoming to her, right? So what Alice now does is she sends the revoke and ACK message, which basically reveals the revocation key of this output to Bob. And now after Bob has received this message, we know these two states are really invalidated. These two are the real new states. And only now the routing process can actually continue. Only now Bob talks to Charlie and sends forward the onion. Or if Bob is the store, can release the pre-image, can do whatever. And can be sure that Bob can actually claim this output even that hits the chain.
How long ago can this go on and they need to keep all the revocation keys?
I'm not sure if I get the question.
How far can this go on? Like new state and revoke, new state and revoke, and everyone needs to keep all the revocation keys.
Yeah, so the thing is also for the revocation keys. So remember when the channel was opened, the channel open message had 5 base points, right? So there was a revocation base point, a commitment base point, a 2 local base point, 2 remote base point, and HTLC base points. So the revocation keys are also derived from each other, right? So technically you only need to remember your last revocation key and you can derive all the previous ones. So, but for this to work properly, you need to like pre-generate like some of the keys, and I think they pre-generate like 2 million or something. So you can do this at least 2 million times. And then of course you could renegotiate or whatever, right? So technically forever. Or at least theoretically forever. But technically maybe not. Yeah, sorry, it's like I'm still a little bit jet lagged. Oh, a really good idea is actually to delete the old states, because then you don't accidentally publish them. But what you do is when you see when you see that the funding transaction of your channel, which you save, it's the chain if it's spent, right? I mean, the funding transaction was on chain anyway, but if you see that it's spent on chain and it's not spent with your most current state, what you do is you take your current revocation key from the other side and you calculate backwards until you find one of those keys that actually enables you to spend the output. Yeah. Yeah, but this is something that you can verify as soon as you receive the revocation key. You can directly see if its child was the previous revocation key. And you should check this, right? I mean, even though these slides are already technical, I still omitted some stuff in the. Yeah. Yeah. The hash? In the penalty transaction, I mean, it's just the penalty path. So it's
transaction on top of a commitment transaction, right? That's what we're describing.
no, I mean, in all stages of the commitment transactions, for all outputs, they all have a penalty path. Yeah. And the penalty path always is the first line in the contract where if you have the revocation key, you can claim it. So you don't need to remember payment hash. I think so, yeah. I think the revocation key is it's on the level of the commitment transaction, yeah. And then all the outputs like have the same revocation key.
So we have to script hash so as a
maybe. Honestly, maybe. I mean.
He's saying pay to script hash. Yeah.
Yeah, I mean, in case of to remote outputs, that's pay to public witness, pay to public key hash, and the other one uncovered by a penalty path are pay to witness script hash. And in this case, for the HTLC output, you need to
keep the script,
the hash and the dialog to be able to recognize the script.
Okay.
Yes.
But then this would mean that every node would have to store all previous HTLC payment hash values? Okay. Yeah, no, I understand what you're saying, but I mean, then when we have to store that amount of information anyway,
yeah.
Then it doesn't make. I mean, it still makes sense to save some part of the key, but I mean, why going through all this burden?
For every HTLC ever added to a commitment transaction.
Yeah, I will double check this.
You stealing the outputs of the commitment transaction, HTLC script, or you stealing the outputs of the HTLC transactions, and for this you also don't need the HTLC output of the commitment transaction.
But at least we are here for another 4 days, right? we can look this up.
I mean, if you can quick vote, I mean, if you are able to directly generate the penalty transaction on top of the part transaction, the part transaction.
It's a reaction, so.
Well, I can put the sledgehammer out here. As far as I understand, with must, we should not have the problem because we can have like separate script paths, but we don't have must yet.
Still need, even in the DAP construction, you need to keep every DAP script.
Yeah, but in that case, you would only want to use the revocation path, right? And that you could construct.
Yes. You just have a DAP script.
In this one, you could construct.
And you can so print the
At least one sledgehammer we have here. All right, no, we should look this up.
Yes, just a vision of this. The scripts that include the revocation key setup record are not in the HTLC outputs of the HTLC second stage. So if you want to steal revoked outputs, you don't need to remember all the HTLC. Yes. The revocation key is used in the two remote outputs, sorry, in the two local outputs and in the outputs of the HTLC
but you may want the other part to use the HTLC success or the HTLC timer to try to recover its answers. Then you may want to also sperm directly on the revocation transaction. And in this case,
yes, but in a standard revocation case, you don't need the script because the transaction you're spending, you don't need the HTLC details to use the revocation.
if the user part doesn't broadcast its HTLC success. I mean, the offered output, receive output, and to local output, you have to local output you don't care because you don't have the route. You need to keep them because if the other part doesn't broadcast, but
I would still suggest to continue with the talk and continue the other discussion either offline or tomorrow, because I think currently it's a little bit difficult to figure this out, interestingly enough. So yeah, I promised you in the beginning that you would understand this like workflow complex graphic by the end of the talk. So if Alice wants to pay David, the first thing that happens via Bolt 11 invoice, the payment hash is being transported back to Alice, and then Alice finds somehow magically a path to David, and then creates the entire onion and starts sending the onion forward. And as I mentioned before, the onion is part of the update add HTLC message. So this blob basically is sent from Alice to Bob, and then Bob decrypts this and sees basically this part and creates a new onion sending over this part. And then we have the final onion arriving for David, and then the pre-image with the update fulfill HTLC messages is being propagated backwards. In this way, the HTLC outputs can technically be removed from the commitment transactions. I think in the implementations, they will just stay there, and the next time they make a new stage, they just omit the HTLC output because they know it's settled. So they don't make an intermediate output where they don't have it, because they know if it hits the chain, they can still enforce it because the pre-image is known. So yeah, this is the workflow in Multihop on the Lightning Network, and I think and hope this was my last slide. So again, there are some pointers. Yeah?
Next question about the key exchange. So
Yeah.
basically the sender of the phone,
So let's look here. The receiver gives up the revocation key first because this one, they say, you know what, I don't care. I can still enforce this. I still have my 20, which I had before. I don't know if I get this one, but even if I don't, I didn't forward anything. Easy.
But if it's, so if it's a payment from Bob to Alex,
Then it's the other way around, right? Yeah.
So it's the sender that initiates the mistake, but it's the receiver that revoke first.
Yep.
and it's because the sender is signing first on the mistake.
Right. Other questions? We discussed a lot already.
You said that we don't remove the
Yeah.
there's no state update until the next time.
Yeah.
Can I see all those?
In C Lightning, I think you can look in your database. So there's an SQLite 3 database, and I think there is. Yeah. Okay. Thank you. But still also in the database, I would say.
You can always go and look into the database.
The database is the
Just
best
to log it,
API.
it will crash your node.
Just make a copy. The database is the best API to C Lightning.
Having an SQL interface to your node.
Yeah. You should document it on the README. No, okay, just kidding.